Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to see how reflections know everything there is to know about isometries. So that's a weird sounding sentence. What I mean by that is that every isometry can be decomposed as the composition of a certain number of reflections. We'll see it's at most 3 reflections are necessary. Obviously, you can stack in more if you want, but you only need 3. And so we'll see that. And we'll also see how isometries are closely related to the idea of congruent triangles. So a pair of congruent triangles uniquely determines an isometry for you. Okay, so let's start with some uniqueness statement. And this uniqueness statement is if I have 2 isometries and they do the same thing to a given triangle, then actually the 2 isometries weren't 2 different isometries, they were the same isometry twice. So in other words, the behavior of an isometry on a triangle explains everything about the isometry. So once you know what it does to one triangle, you know what it does to everything. So here's a precise statement here. So we suppose that triangle ABC is a triangle. And then we suppose we have 2 isometries, T and T prime. And they have the property that their images of the point A are the same, the images of the point B are the same, and the images of the point C are the same. So under this hypothesis, then the 2 isometries are actually the same for every other point in the plane. Now let's look at a special case of this first. Let's suppose T prime is the identity. So in that case, we just have basically one isometry, and we're comparing our isometry T to the identity isometry. And so we have T of A is A, T of B is B, T of C is C. And then the claim we make is this forces T to be the identity. Okay, let's prove this theorem. So the key idea of this proof is we want to exploit the fact that an isometry sends every triangle to a congruent triangle, to the one we started with. That's the first thing. And the second thing is that isometries preserve all the geometric structures that we know and love. So things like betweenness, lines, segments, things like that, right? So the image of a line is a line, that kind of thing. Okay, so let's start with what do we need to show? We want to let P be a point in the plane. And what we want to show is that T of P is itself. So let's go ahead and introduce a name for this point. So I'm letting P prime be T of P. And then our goal is to show that P prime equals P. Now we have 3 points where this map does nothing, right? The image of A is A, the image of B is B, the image of C is C. So it's not interesting if P is one of those. So we can say without loss of generality, P is not equal to A, P is not equal to B, and P is not equal to C. Right? If it's equal to one of those, we're done and it's wasting our time. Okay. So now P is not one of the vertices of the triangle, which means by the one of those theorems that you had on your midterm study guide, which is that if I have a pair of lines in incidence geometry that are distinct, they intersect in at most one point. Or, as you saw previously, the 3 sides of a triangle, right, if I extend them to lines, there is no point that is incident to all 3 of them. Right, so this is, we have then, right, so P is not incident to all three of these lines AB, AC, and BC. And what we're going to do is we're just going to prove it in the case where it's not incident to the line AB. And after changing letters, we can deal with the other two cases as well. So we'll say, without loss of generality, P is not incident to AB. Okay, so P is not incident to AB. I'm going to draw a little picture here. And here I have a point P. And the claim I want to make is that that either P and P prime on the same side of AB as the point C, or they're both opposite to C. And so what I'm saying is, let's say the point C is over here on this side, then P and P prime have to be on the same side. Right? That's my first claim that I make. So let's go ahead and prove that. Why is this the case? Right? So the reason is we have, so we're going to consider the intersection of the segment and the line AB. So they intersect if and only if C and P are on the same side. Right? That's our definition of being on one side or the other of this line. Okay, so now let's consider the image of the segment PC and the image of the line AB. Well, the image of the segment PC is the segment between the images of P and C. So that's going to be the segment P prime C, remembering that the image of C is itself. And the image of the line AB is just itself as well. On the other hand, by the fact that isometries preserve all of the geometric structures we're interested in, the number of intersections of those two things is the same as the number of intersections of the segment PC and AB. And now from this, that means, right, we have 0 intersections if P and C are on the same side, and 1 intersection if P and C are opposite. So that forces, similarly, P prime to be on the same side as P. Okay, so that establishes our claim. So now we're ready to hit this with the our triangle fact. And so now we have triangle ABP is congruent to triangle ABP prime, and P prime are on the same side of the line AB. By uniqueness of angles, and this is very similar to what we did with the side angle side congruence. So by uniqueness of angles, we have then that the ray AP equals the ray AP prime, and the ray BP equals the ray BP prime. And hence, P prime is at the intersection, or I should say in the intersection. There might be in the intersection of the line AP and BP. These two lines are distinct, and hence, right, so these two lines are distinct. So P prime has to be the only point of intersection between them, which means it has to be P. That proved this special case where T prime was the identity. Now we can get the whole theorem as follows. What we do is we say, and so now let's look at the general case. We have isometries T and T prime, so that T of A is T prime of A, T of B is T prime of B, T of C is T prime of C. Then we apply our special case to the composition of T prime with T inverse. Right, if I look at T prime composed with T inverse, I get that A maps to A, B maps to B, and C maps to C, and hence T prime composed with T inverse is the identity, so that means that T prime equals T. And now we're truly done with our theorem. And that's the end of this proof of the fact that an isometry is entirely determined by its behavior on a triangle. So now the next thing we're going to look at is how to extend this so that every congruent triangle, every pair of congruent triangles gives us an isometry.